Hi, I'm Joel Sercel, CEO and founder of TransAstra Corporation, and I'm the PI on the Lunar Polar Propellant Mining Outpost, NIAC Phase 2 study that we're doing in an accelerated fashion in 1 year to support the NASA Artemis program. The first innovation I'll be talking to you about today is the sunflower power tower concept. If you put a solar reflector on a tall tower on the moon, it has a couple of profound benefits. If you're near the lunar poles, it tremendously increases the duty cycle of sunlight hitting the top of the tower. And so you can use solar power in the lunar poles in lots of places that you wouldn't otherwise be able to have power. Secondly, you can put transmitters for beamed energy at the top of those towers to get beams over the topology and vastly increase the utility of power beaming on the moon. This is an example of the type of analysis that shows the power of the sunflower tower. On the left, you can see the illumination. This is averaged over a year near the lunar North Pole at the surface level. On the right, you can see if you were 1,000 meters AGL above ground level, what the illumination can be. And you can see that the illumination shifts from being mostly dark and certainly not feasible for solar power to mostly light and certainly feasible for solar power. And then if you look at the duration of eclipse periods, on the left, you have virtually 100% blackout, the dark yellow, near the surface over the course of a year. But if you look at the longest blackout period above the surface, if you're in a tower, it's just a couple of days. And that becomes a very reasonable energy storage requirement. So the concept here is that you put a very, very lightweight, thin film reflector, possibly supported by an inflated frozen ring at the top of the tower. These can weigh a few kilograms for reflectors the size of a tennis court. And then you suspend that on a tower and reflect the sunlight down to solar panels that can be located near the base of the tower so that you don't have to support them above ground level. We did some analysis to figure out how big of a tower you can make on the moon and what the payload fraction is. This is with off-the-shelf materials with reasonable safety factors. What you find is that it's actually practical to make self-deploying towers on the moon that can go up to 1 kilometer in height. At 800 meters, you get a payload fraction of about 30%. What's really cool is you don't have to go to a 1,000-meter tower to get great improvements on the moon. NASA is specifically interested in the South Pole. So here's some South Pole data that shows the fractional illumination at the surface near the South Pole. Inside the red rings are permanently shadowed regions. Most of the cold traps are inside those red rings. And what you can see is that at the surface, anything close to a cold trap or permanently shadowed region, there's just no illumination. This is average illumination over a year as the moon tilts and wobbles in its orbit around the sun, or around the Earth. 100 meters AGL above ground level, you can see the illumination situation is completely different. And instead of just a few peaks, craggy peaks where you could put a laser transmitter or something, and then miles away you can build an outpost, you can see that you can actually have lots of places that are just right adjacent to very modest topography, where there's permanently shadowed regions and cold traps, where you could realistically put an outpost, and yet the duty cycle is now over 50%. So 50% duty cycle is what you have at the lunar equator. But what's really cool also about the duty cycle that you get from 100-meter towers near the lunar poles is that 50% duty cycle isn't like 14 days of light and 14 days of night. The duty cycle is just interruptions from the lunar topography. So you don't have to have such a massive energy storage facility. We've also looked at, well, what could you do with a 10-meter tower to demonstrate the basic technology? A 10-meter tower with a solar reflector at the top that can produce kilowatts of power. That 10-meter tower is only kilograms. It's something that could easily be flown on Eclipse lander for a tech demo, for a multi-kilowatt tech demo. And even a 10-meter tower gives you a significant improvement in solar duty cycle. But more important than that, 10-meter tower vastly improves the topography that a laser transmitter can see, so that if you have rovers and landers in the area, you can power them with high duty cycle way out into the surrounding landscape. This is an example actually of the cold trap labeled A on this figure near the South Pole, of how much the view shed. View shed is a term for how much land you can see as a function of tower height. And on the left, you see the topography. The gray area there is the permanently shadowed region. On the right is the same map viewed from above that shows the view shed from a tower located where the purple star is on the left. Inside the white line is our estimate of where we have a cold trap with lots of ice for mining. There's enough ice in this little area here that if it's just 2% ice in the cold trap, it could maintain a lunar outpost for many decades of water to make propellant from it. What you can see is the orange area is the area that's visible with no tower. If you don't have a tower, laser power beaming doesn't work. If you just have a 10-meter tower, it opens up a huge area for rovers and mining experiments. And then later, when you want to start mining operations, a 100-meter tower, which is really quite modest from an engineering perspective, actually opens up virtually the entire cold trap where the ice is going to be. So you can completely run all of your mining operations from there and your mining rovers. The type of mining rover that we've been studying, we think is a huge breakthrough. Is based on our invention of radiant gas dynamic mining, which doesn't require excavation. It does subsurface heating to heat well below the surface where the ice is, even if there's a dry overburden. And then that drives the vapor up into the domed rover, into the center of the rover, not near the edges. And then you capture the ice there with our patent pending rotary cryo belt. We've done design work on what the rover could look like and concluded that we could fit probably 3, maybe 5 of these at the 5-meter scale in a single New Glenn launch. And each one of them, our estimates suggest, could mine up to 100 tons of ice. The experiments that we'll be doing in the dusty thermal back chamber at Michigan Tech with Paul Van Sassante, the idea here is that it's a 2-meter class, liquid nitrogen cooled, high vac chamber that you can put 1,500 kilogram simulant beds of lunar simulants. So it's big enough and deep enough to get scale. Experiments at smaller scales are probably not valid based on the work that we've done. And we can put a 1 to 1.2 meter dome inside this, raise and lower the dome inside. And we're in the stages right now of developing that dome that'll have 7.5 kilowatts of microwave power. This is the experimental apparatus from what we've done so far. What you can see is we've integrated what's called a broadside array, which is a type of microwave array, into a section of dome that's at the same radius of curvature as a 1.2 meter diameter dome for testing in the dusty thermal back chamber. We've thoroughly measured the intensity field pattern of S-band radiation. Our subscale work will be at S-band. Our operational rover will be at L-band, 912 megahertz roughly, because you get more penetration that way. This is the experimental data from the field intensity maps we've been making. These maps feed directly into the design of the dome for the experiments that we'll be doing in a 1.2 meter dome at cryogenic temperatures with high fidelity lunar simulant and 7.5 kilowatts of microwave power. What you can see here is taking our experimental data and mapping that in 3-dimensional space to an intensity map. What you see is on the left, you see the intensity map at the surface, and then 25 centimeters below the surface, 50 centimeters below the surface, 75 centimeters below the surface. The point is you need to have large-scale experiments to really get to heating below the surface in case there's a dry overburden. And this is what the field intensity looks like. The blue line is in free space. The orange line is with our calculated attenuation due to coupling to the lunar regolith. Our fleet of mining rovers. So sunflower towers solve the power problem at high lunar latitude in many locations, and radiant gas dynamic mining solves the water collection problem, but they're at low TRL, so we're doing a crash program to increase their TRL right now. Thank you.